Professor Belfrost's computer science class is back!
Hi, welcome back. And here's Professor Belfrost's class on computer science. And today we are going to explore another concept on computer science, continue our last lesson. And if we are already ready for today's episode, then let's go. Well, today we'll start a new chapter, which is the chapter on RISC. So actually, there are two terms that we will explain in this chapter, in this lesson, which are RISC, which is reduced instruction set computers, and CISC, which is complex instruction set computers. But let's see the outline of the chapter first. So we will discuss the instruction execution characteristics, the use of a large register file, compiler based register optimization, RISC, RISC pipelining. Maybe these two will skip, and they will discuss about RISC versus CISC controversy. But maybe half of this will be made into a new video. Okay, the next lesson. Okay, let's see the key points that have been summarized by the writer of the author of this book. So, yeah, studies of the execution behavior of high-level language programs have provided guidance in designing a new type of processor architecture and reduce instruction set computers. So, maybe I want to highlight this. Yeah. So assignment statements predominate, suggesting that the simple move of data should be optimized. And there are also many event instructions which suggest that the underlying sequence control mechanism needs to be optimized to permit efficient pipeline. Okay. In studies of operand reference patterns suggest that it should be possible to enhance performance by keeping a moderate number of operand registers. And the studies have motivated the key characteristic of RIC machines. First, a limited instruction set with a fixed format. Second, a large number of registers are the use of compiler that optimize register usage. And third one is an emphasis on optimizing the instruction pipeline. So the simple instruction set of RIC lends itself to efficient pipelining because there are fewer and more predictable operations performed per instruction. RIC instruction set architecture also lends itself to the delayed branch technique, in which branch instructions are rearranged with other instructions to improve pipeline efficiency. Okay, let's see. This is not very important. Yeah. So, uh, RIC, there are some key elements shared by most designs, though actual RIC system can be implemented in a variety of ways by different groups. So there are three things here. The first one is the large number of general purpose registers and or the use of compiler technology to optimize register usage. The second is a limited and simple instruction set. And the third one is an emphasis on optimizing the instruction pipeline. Okay. Now let's see the instruction execution characteristics. Um, okay, let's see here. So the response from research and and industry so far has been to develop even more powerful and complex high-level programming language. Okay, maybe I will uh, make it short from now on HLL. Okay, so I will use the term HLL to state high-level programming language. Okay, so this HLL allow the programmer to express algorithms more concisely and take care of much of the detail, and often support naturally the use of structured programming or other object-oriented design. And also, but the solution gave rise to another problem, which is called semantic gap. Okay, this is the difference between the operation provided in HLs and those provided in computer architecture. Okay, and this uh, are alleged to include execution inefficiency, excessive machine program size, and compiler complexity. Okay, and such complex instruction sets are intended to ease the task of compiler writer, improve execution efficiency, provide support for even more complex and sophisticated HLs. Meanwhile, a number of studies have been done over the years to determine the characteristics and patterns of execution of machine instructions generated from HL programs, and the result is that we need to look for a different approach, namely to make the architecture that supports the HL simpler rather than more complex. And to understand the line of reasoning of RAC advocates, then let's see. Here are some points. The first one is operation performed. And this determines the function to be performed by the processor and its interaction with the memory. Okay, so the first one. Second one is operand used. The types of operands and the frequency of use determine the memory organization for storing them and the addressing modes for accessing them. And the third one is execution sequencing. And this will determine the control and pipeline organization. So let's explain one by one. Okay, for operations. Okay, so let's see which one is the important. Okay, actually this is not very okay. Also have operands. Yeah. Actually, this is just a research result, so I will skip it until I find something that is important. Procedure calls, not very important. This is just a research article, I think. Implication. This is the implications. This is the last one. So, yeah, here. So, a number of groups have looked at results such as those just reported, okay, the paragraphs above, and have concluded that the attempt to make the instruction set architecture close to HLS is not the most effective business strategy. Rather, the HLs, the HLs can be supported by optimizing performance of the most time-consuming feature of typical HLL program. And generalizing from the wealth number of researchers, the three elements emerge the characteristic RISC architecture. Here's the highlight. So first, use a large number of registers or use a compiler to optimize register usage, and this is intended to optimize operand referencing. Okay. Second, careful attention needs to be paid to the design of instruction pipelines, and because of high proportion of conditional branch and procedure call instructions, a straightforward instruction pipeline will be inefficient, and this manifests itself as high proportion of instructions that are prefetched but never executed. And the third one is that a simplified instruction set is indicated, and this point is not as obvious as the others, but should be clearer when we discuss this lesson later. Okay, so maybe I'll go. Okay, so here's the important. A strategy is needed that will allow the most frequent access operands to be kept in registers and to minimize register memory operations. There are two basic approaches which are possible, one based on software and the other based on hardware. So the software approach is to rely on the compiler to maximize register usage, and a compiler will attempt to allocate registers to those variables that will be used the most in a given time period, and this approach requires the use of sophisticated program analysis algorithms. Whereas the hardware approach is simply to use more registers so that more variables can be held in register for longer periods of time. But we will start the discussion from hardware approach first. Okay, so here's the important thing. Okay, we have register windows. Because most operand references are two local scalars, the obvious approach is to store these in register which will have a few registers reserved for global variables. And the problem is that the definition of local changes with each process call and return operation that occur frequently, which on every call that local variables must be saved from the register into memory so that the register can be reused by the call program. And also the parameter must be passed, and on return the variable on the parent program must be restored and result must be passed back to the parent program. So here's the solution. First, a typical procedure employs only few pass parameter and local variables, as can be seen in table 30.4. Where is 30.4? Maybe later. Okay. And then second is the depth of the procedure activation fluctuates within a relatively narrow range which is shown in figure 4.21. Oh, it's not in this chapter. Okay, no matter. So to exploit these two properties, that multiple small sets of registers are used. So a procedure call automatically switches the processor to use a different fixed size windows of register rather than save your register in memory. And the concept is well illustrated in the figure below. You can see here is the overlapping register windows. And as can be seen, at any time, only one window of register is visible and is addressable as if it were only set of registers. And the window is divided into three fixed size areas in this case. Okay, so parameters register hold parameters passed down from the procedure that call the current procedure and hold results to be passed back up. So here's the parameter registers. You see parameter registers. Then local registers are used for local variables. Okay, so here's the local variables, local registers, and then we also have temporary registers, which are used to exchange parameters and result with the next lower level, as can be seen. Yeah, good to go. And to handle any possible parent of calls and returns, that the number of register windows would have to be unbounded, and instead the register windows can be used to hold the few most recent procedure activations. And the older activations must be saved in memory and later restored when the nesting depth decreases. And thus, the actual organization of the register file is a circular buffer, as shown in the figure below. Okay, maybe, yeah, this is the figure that shows us how to do a circular buffer organization for an overlap windows. Okay, so we have a kind of restore when we are going counterclockwise, and for going clockwise we are doing save. Okay, maybe I'm not going to that, but for this, let's see if there's some important concept we need to explain here. Okay, done. So we are now going to global variables. So the window stream just described, yeah, it provides an efficient organization for storing local scalar variable in a register, but the scheme is not. It hasn't addressed the need to store global variables, those accessed by more than one processor. And actually, there are two options that can be suggested for this. The first one is that variable declared as global in an HWL can be assigned memory location by the compiler, and all machine instructions that reference these variables will use memory reference operands. This is very straightforward. And another alternative is to incorporate a set of global registers in the processor. And these registers will be fixed in number and available to all procedures. And a unified numbering scheme can be used to simplify the instruction format. And here we'll review about large register file versus cache. So the register files organized into windows as a small phase buffer for holding a subset of all files that are likely to be used the most heavily. And from this point of view, that the register file acts much like a cache memory, although a much faster memory. But here's a question that arises, is to whether it will be simpler and better to use a cache and a smaller traditional register file. So here's a table that shows you a summary of characteristic comparison between these two approaches. So the left side is for large register file and the right one is for the cache. Okay. So yeah, here's the register file should save time because all local scale variable are retained. On the other hand, a cache may make more efficient use of space because it's reacting to situation dynamically. Furthermore, caches generally treat memory reference alike, including instruction and other types of data, and thus saving in these other areas are possible with a cache and not a register file. A register file may make inefficient use of space because not all processors will need the full window space allocated to them. On the other hand, the cache suffers from another sort of inefficiency that data are read into the cache window. And whereas the register file contains only be so many global scalars, but only few of them are heavily used. Okay. However, it's difficult for compiler to determine which global will be heavily used. But with the register file, then the move of data with the register and memory is determined by the procedure of nesting depth. And because this depth usually fluctuates within a narrow range, and the use of memory is relatively infrequent, and most case memory are set associated with small set size, and thus there is a danger that other data or instruction will override frequently used variables. And based on the discussion, the explanation that come so far, the difference between a large window-based register file and a cache is not clear-cut, because there is actually one characteristic in which the register approach is clearly superior, and which suggests that a cache-based system will be noticeably slower. And this distinction shows up in an amount of addressing overhead experienced by the two approaches. Okay, so here's the figure that shows the difference. Okay, you can see. And here's the explanation. That to reference a local scala area window-based register file, the operator register number and Windows number are used, and this can pass through a relatively simple decoder to select one of the physical register. And to reference a memory location in a case, then a full with memory address must be generated, and the complexity of this operation will depend on the addressing mode. Okay, thus, from the point of view of performance in the window-based register file is separate from local scalars, and further performance improvement could be achieved by the addition of cache for instruction on. Then we'll see a little about compiler-based register optimization. Okay, so here, each program quantity that is a candidate for residing in a register is assigned to symbol of virtual register. Then the compiler then maps the unlimited numbers of symbol register into a fixed number of real register. Symbol register whose usage doesn't offer can share the same real registers. And let's see, if in a particular portion of the program there are more quantities to deal with the real register, then some of the quantities are assigned to memory location, and load and store instructions are used to position quantities to register temporarily for computational operations. And maybe we can see the graph. Okay. Actually, maybe you can read this by yourself. Okay, actually we have done with this one. Okay, a little more. So we have noted the trend to reach instruction sets to include a large number of instructions and more complex instructions. Two principal reasons also have motivated this trend. The first one is desire to simplify compilers, and so the second one is desire to improve the performance. But it is not the intent of this lesson to say that the CIC designers took the wrong direction, but because technology continues to evolve and because architecture exists along a spectrum rather than in two neat categories, that black and white actually is unlikely ever to emerge. Okay? So, let's see. The first of the reason is that combined simplification seems obvious. And the task of the compiler writer is to generate a sequence of machine instructions for each HL statement. And if there are machine instructions that resemble HL statements, then this task is simplified. Okay. The other major reason cited is that the expectation that a CIC will yield smaller, faster program. Okay. And there are clearly two advantages to smaller programs. First, because the program takes up less memory, and there is a saving in that resource. And with memory today being so extensive, that this potential advantage is not longer compelling. But more important, that actually small programs should improve performance. And this will happen in two ways. First is fewer instructions mean fewer instruction bytes to be passed, and second, in a paging environment, then smaller program occupy fewer pages, reducing page faults. But the problem with this line of research is that it is far from certain that a CIC program will be smaller than corresponding RIC program, because in many cases the CIC program expressed in symbolic machine language may be shorter, but the number of bits of memory occupied may not be noticeably smaller. Okay? Maybe the table show you result from 3 studies that the author of this book have prepared for us. But there are several reasons for this rather surprising result. Okay, it's noted that compilers on CIC tend to favor simple instructions so that the conciseness of the complex instructions seldom comes into play. Also because there are more instructions on CIC, the longer opcodes are required, producing longer instructions. And finally, RIC tends to emphasize register rather than memory reference, and the former require fewer lists. Okay, so the expectation that CIC will produce smaller programs with the attendant advantages may not be right. And the second motivating factor is for increasing complex instruction set was that instruction execution will be faster. And yeah, it makes sense that a complex HL operation will execute more quickly as a single machine instruction rather than a series of more primitive instructions. But because of the bias word the use of the simpler instruction, that this may not be so. Okay, the entire control unit must be made more complex, and or the microprogram control store must be made larger to accommodate a richer instruction set. And either factor will increase the execution time of the simpler instruction. Okay, and yeah, I think maybe I'll stop till here for today, and we will continue the next lesson to explain the RAC in more depth. Yeah. Yeah, before I end this, I have a quote for you for today. So Muhammad Ali once said, "Don't quit, suffer now, and live the rest of your life as champion." And that's all our lesson for today. Thanks for watching, and here's your to-do list. So please subscribe, give a like, comment, and share this video to your friend. I'll be back on every Monday on the same class in computer science. And don't forget to visit our website at https ://science with xyz.unaux.com. Keep watching and be thoughtful. Goodbye. See you on the next episode.